Right. So I would like today to introduce the statistical finite element method. This is a work which we have been doing with Mark over the last 1 year. And in addition to both of us, there are, why does it go to the next page? So there are two RAs working on that. These are Eke Fabrianto and Guy Yin. And in addition to this core team, we have several early stage PhD students who are looking in the extensions and applications of this method. So as Jennifer briefly mentioned, so the motivation for this work comes from the limitations of current deterministic mathematical and finite element methods, which are used in the design of engineering systems and structures. And as we know, we have in practice uncertainties related to the material, loading, geometry, and so on. And currently, the deterministic model do not take this into account in a first instance. But later, they essentially they are implicitly taken into account by using some through codified safety factors, which leads to over-dimensioning of structures. So if we want to design more efficient and structures and make more rational decisions about their operation, we need more accurate and reliable predictions. And in order to do that, fortunately, we have more and more in situ monitoring data of engineering systems like the ones collected by CSIC, which enable us to capture uncertainties in a real structure. So I have included here a few examples. These are not obviously not my examples. I mean, we do just computations. We don't do experiments. So the first picture on the left, this is you can see a spanner, and then overlaid to that, you can see in color the strains or measured strains obtained with digital image correlation. And in the next picture, so this is one from CSIC, where fiber optic sensors are used in order to measure restraints in train sleepers. And so the scale, as you can see, when we get from the left to right, the scales get larger and larger. So on the most right, you can see essentially city scale sensing of strains using satellite data. Okay. So the objective, the research objective is here to develop a statistical framework which enables us to synthesize data, observational data with finite element predictions. So in this cartoon, you can see we have a real system, like the bridge, railway bridge shown. Then we have a finite element model, like on the right. And then we have data. So essentially what we would like to, we have, obviously we don't know a real system, we don't know its behavior. So what we have is we have a finite element model, then we have a data, and we would like now to synthesize data and finite element model in order to infer the real system behavior. So this is I think a quite simple motivation, And but there are several challenges associated with this. One of them is essentially the finite element models are misspecified due to various modeling assumptions. Because in order, as every engineer knows, we're starting from a real system. In order to get to a finite element model, we make many assumptions about the connections, supports, and so on. So in addition to this mis-specification errors, also we have uncertainties, like in material, loading, geometry, I mentioned before. Okay, and in addition to that, now in the engineering context, data is usually scarce. In engineering, we don't have that much data. We don't have like in deep learning also, where we have terabytes of data. Our data is quite limited. So In order to take account these uncertainties in the data model parameters and the model itself, we use a statistical modeling approach. And in the statistical approach, any uncertainty is represented as a probability. And what this means in practice is essentially we end up with a set of random variables, and each random variable has a corresponding probability density function. Okay, so we have a finite element model. I mean, this is just a cartoon example, right? For a system with only one degree of freedom. So essentially, a finite element model, this is the probability density function. So it has a mean, and this has some sort of variance. But, I mean, this is I chose here essentially a Gaussian. Then we have on the slide the noise, observation noise, which is usually given. Then we have this data. For the data, we have obviously just points. And we want to now use all these probability distributions and the underlying model, statistical model, in order to infer the real system probability density, which we do not know. Okay. So this is an outline of my presentation. So first I want to introduce our statistical data generating model. And then the prior probability densities, which are important in this framework. So the prior probability density of a finite element solution and the model reality mismatch. And using Bayesian inference, we can update this prior probability densities and obtain posterior probability densities. So at the end, I have two examples. So one is a one-dimensional verification example, and the last example is a larger example. This is about the Staffordshire bridge. I mean, the bridge is obviously missing. So it's not just Staffordshire. Okay. So, and after here, I have there is time to ask questions after the prior probability densities. So this is our statistical data generating model. So we take a data vector. So data vector is always y in these slides. And we decompose it into several components. First, we have this Z. Z is a true system response. E is a observation noise. Okay. So this is standard, real system behavior plus the observation noise gives us the sensor reading. So next we decompose this real system behavior set into two components. So one consisting out of U. U is always finite element solution here, and D is a model reality mismatch. Okay. And then I have here additional parameters. I mean, I have to include them for consistency, but they are not important. P is a projection matrix. This is related to essentially, if you do finite elements, in elasticity, our unknowns are displacements, but usually we measure strains, right? So we have P maps the displacements to the strains. And the rho is a scalar parameter, is a model parameter, which we will determine later. So in this decomposition, we are assuming that each random vector, so I mean y, z, e, and so on, these are obviously vectors. And so with each random vector is normally distributed. So essentially we have, so if you remember, I mean, if for a Gaussian or a normally distributed field is fully described by its mean, and its covariance matrix. So we have for the finite element solution, essentially we have a mean of U bar, and this is CU is our covariance matrix. I mean, the other quantities have similar normal distributions, like you can see here. I mean, this is, of course, an approximation that we are approximating as normals. However, I mean, in practice, it is an approximation which makes the computations easier. But in practice, in many cases, this gives a very good approximation. Okay, so now we have essentially We usually know observation noise. It's statistics. It's a characteristic of a measurement device we are using, right? But we don't know usually the model mis-specification, and we don't know yet the finite element, the distribution or the density of a finite element solution. So we need to determine that. So first we look at the finite element solution. So the density for a finite element solution we obtain with a probabilistic finite element method is a classical technique. So, I mean, I have here some equations. I mean, you don't, I have maybe too many equations, but you don't have to look into details. I mean, it's important is a general idea. So this is our governing equation. Let's say this is our heat equation, heat conduction. So U will be here a temperature, and kappa is like a diffusivity, a random diffusivity, and F is a random loading. So then we do a usual finite element analysis or finite element discretization, and we obtain this equation. A is a system matrix, like stiffness matrix, U is a temperature vector, and F is the loading. So this is a standard. Now, essentially, as mentioned, our diffusion coefficient and the loading are random. So usually, I mean, in engineering, we know we can kind of, we know what is the mean of a diffusion coefficient, which is kappa bar, we can say that. In addition to that, we also know about the statistics of this field, like the standard deviation, correlation length, and so on. So these are given. So we would like now to use this information and introduce it in the finite element solution, and or finite element discretization, and obtain essentially the probability density for U, the temperature. Okay. So after some algebra, I mean, which is straightforward but slightly tedious, so we obtain this normal distribution for the finite element solution. So it has this mean, and this is a covariance matrix, and these are the equations. I mean, especially the covariance matrix looks quite long and so on. But I mean, you do this only once, and this is somewhere hidden under somewhere in the finite element code, and a user never has to see that. Okay? So just an example of what we have been doing on the last slide. So we have this one-dimensional problem, heat conduction, and we have domain 0 to 1, and we have given a temperature on the left and on the right, 0 and 1 is 0, and the loading is now, we have random loading with a mean 1, and we have some variance or standard deviation. I mean, it's obviously, so variance is 0.1, and then we have a correlation length given. So essentially F is a random field. So I have plotted here in this left plot the loading over the domain. So it has a mean of 1, and then you can see also here is the essentially this 95% confidence region. And in addition to that, we have sampled here from a real field, I mean from this Gaussian process, or from this normal Gaussian distribution, we created several samples, and these are the different lines, okay? So these are kind of temperature loadings which we would expect in this problem. So these are 5 lines. For each one, we solve this finite element solution. It solved the finite element model and obtain a temperature distribution, which is shown on the right, okay? So these are the lines are color-coded, as you can see. So essentially, there's a long equation on the last slide, which enables us is to compute the mean of a finite element solution, and also essentially it's a 95% confidence regions by just looking at this at the statistics of loading. So. So now we have some distribution for the finite element solution for the temperature, let's say. And now the other missing distribution was, or density was the model mismatch. So model reality mismatch, the difference between finite elements model and the reality. And this is due to the usual engineering simplifying assumptions related to the boundary conditions and so on. And here we have some irreducible errors. So we model that with a random variable. And this is the other variable in our decomposition, D. So we assume that this has also a normal density, like this one. And here, essentially, the mean is 0. And the covariance matrix CD, we obtain it from a chosen kernel at the essentially, this is a squared exponential kernel, which we evaluate at the observation locations in order to obtain this matrix CD. Of course, I mean, we chose this kernel, but you could choose other kernels. And this implicitly essentially assumes certain assumptions which we make about the type of model reality mismatch. But one could use other kernels, but one could also completely automate this process of choosing other kernels. That's also possible. So I think I didn't mention it yet, but essentially in this, we assume this type of kernel, but this parameter sigma d and LD are two hyperparameters, unknowns, which we will estimate from the data. Okay, so sigma is a scale parameter, and it's related to a standard deviation or variance. And LD is a length scale parameter. This is kind of a correlation length for the components of a vector D. Okay, so summary so far. So far I didn't talk about, we didn't integrate, make use of data yet, right? So we are just talking about the model, which is based on this decomposition of a measurements into a finite element component U, a mismatch component D, and the sensor noise E. Okay, and then we said we derived, or we looked at the densities of this random variables U, D, and D, finite element solution, model mis-specification, and measurement noise. Okay, so we have a few parameters here. These are sigma d and LD, and then we have also this rho. So these are called hyperparameters, and we have to, which we also don't know yet. So we have to determine them. Okay. So maybe if you have questions, I can answer regarding the model at this point. If I can, I don't see anyone. Looks like, okay, there is more. What is that? Chat. So there is no question? Oh, there's a question. Ashwin, so do I enable that?
If you'd like to unmute yourself to ask your question.
Ashwin?
Yeah, thanks for that. I'm just wondering if you, in your model, have any uncertainty around the physics, or you assume that the physics is precise?
Essentially, this model reality discrepancy models the uncertainty in the choice of a model. Does it make sense?
So, okay, I see. Okay, so okay.
Yeah. So, any other questions? No. Okay. So, how should I close this? So, okay, so we have our model and with random variables, and we have essentially some prior densities before seeing the data. So now we would like, now we introduce the data. Okay, So essentially now we can, we use Bayesian inference in order to update the prior densities on the previous slide, and also to determine the hyperparameters in light of the observation data. So this is a celebrated Bayes formula. I mean, this looks this is straightforward to derive. And here, I mean, essentially what we have is maybe start. So on the left-hand side, we have the updated finite element density. So here bar means everything on the bar, right of the bar is kind of known or given. And U is our random variable. So the density of a finite element solution given data Y and given hyperparameters rho, sigma, L. Okay. And this is our updated finite element density. And here on the right, we have the PU. This is our prior density for the finite elements, which we obtained essentially probabilistic finite elements method, which I showed you on the previous slides. And then we have, in addition to that, a data likelihood term. So, which essentially, this tells us essentially for a given model and finite element, model parameters and finite element solution, what is the probability of observing certain data Y, okay? And then we have a marginal likelihood. So this is a denominator term, and this is essentially the probability of observing data Y or average over all possible finite element solutions U. Okay? And one side comment, because our essentially we have been using all Gaussian or normal distribution. Now all these terms like the likelihood, data likelihood, marginal likelihood, and so on are all essentially have closed form expressions. They are normal distributions. So, and the advantage of having normal distributions is we can essentially derive closed form solution. So for the essentially for the posterior or for the updated finite element solution, we obtain after some maths and algebra, we obtain essentially this normal distribution with a mean vector shown here, and with covariance matrix shown here. So this bar indicates always a mean after we know the solution Y, right? And the covariance after matrix after we know the solution Y. So, I mean, the computation of this mean covariance and so on requires the inversion of large matrices. So there is some numerical issues which I will not discuss today. And okay, so after we have a finite element, posterior finite element, updated finite element solution, we can also compute the posterior or true system density, which is shown here. It's again a normal distribution. Here we use this relationship. Again, this here you see again the same mean vector and covariance matrix as above. So we had also some hyperparameters like this rho and then sigma and L, which are related to this mismatch covariance. And so we determined that from the marginal likelihood. Remember, the large marginal likelihood was a denominator in a denominator of the Bayesian formula. And it tells us the probability of observing the data Y over all possible finite element solutions. So we have again a closed form solution for that. It's expression for that is a normal distribution. So we can now obtain these other parameters, this rho, sigma, and LD, by maximizing the marginal likelihood, or we can essentially take this marginal likelihood and sample it with market chain Monte Carlo, and we take then the empirical mean. So in the examples which I will show now, I will use this second approach. Okay? So we sample the marginal likelihood with Markov chain Monte Carlo and compute the from the samples the empirical mean. Okay. So some examples. So first example is kind of a verification example. And it's similar to a one-dimensional illustrative example which I showed. So it's a one-dimensional problem, Poisson-Dirichlet problem with random forcing. Let's say the heat equation, right? And over a domain from 0 to 1. And only the loading is random, F is random. And this has this given random distribution, or is a Gaussian process with essentially with a mean 1.97 and 0.3 is the variance. And then we have this 0.25, the essentially a length scale parameter. So if we plot that, so this is F over the domain. So we have its mean and we have its 95% confidence region. Right? So we can, if you consider this, this is essentially, we can use now a forward problem and use this equation which I introduced in order to compute the mean of a finite element solution, which is a blue line, and also the confidence region for the finite element solution corresponding to a random loading like here, like on the left. Okay. So this is the blue is our finite element solution, and we are assuming a true system density, which is this black line and this gray region. So you can see that the black line, the real system behavior has more detail than the finite element solution, right? The blue curve, and then the variance is of course also different. So essentially, we use this. So in terms of observations, so we have variable number of observation locations. Our domain goes from 0 to 1. So we have either 4 observation locations, sensors, 11 sensors, or 33 sensors. Okay, so these are different cases which we will look in turn. Then at this sensor locations, we essentially generate observations, synthetic observations with the given real system behavior, which we assumed on the previous slide, the gray and black, gray region and black curve. And so here, this is our sensor readings, and this is our 2.5 10 to the power minus 5 is essentially the sensor accuracy. And at this, at the observation, at each of these observation locations shown here, we sampled now many repeated readings, which go from 1, 10, 100, or 1,000. Okay, so we change the number of sensor locations and the number of readings at each this location. So for each combination, obviously we can use the statistical finite element method to compute the posteriors or updated finite element solution and to infer the true system behavior. Before we do that, so for each case we determine first the hyperparameters, rho, sigma, and L associated with our statistical model. So I have here plotted only the case where we have 11 observation locations and different number of readings. Okay? So here on the left we have a rho parameter, sigma parameter, and L parameter on the right. So if you look at NO, this means now we have 11 observation locations and we make at those locations only just one reading. So then you can see this marginal likelihood or the probability, the histogram, which we obtained with MCMC or Markov chain Monte Carlo. So you can see that it is very broad. Okay, it doesn't have obvious maximum. So I mean, rho can be here anything. I mean, we don't have any confidence about its exact value. And the same, the sigma is also quite broad. I mean, this L is a little bit more focused, right? But one reading seems to be, in this case, not enough. So if we now make 10 readings at each of these 11 locations, so then we get this, this densities histogram starting to get more focused, right? But if you make like 100 readings, then we are very, we have a well-defined maximum. And if we increase the readings more and more, even more, and they have 1,000 readings, so then we have this blue histograms. Okay, so we have a very well-defined mean, and we have also very small variance. So we can be quite sure that the true parameters are those. I mean, we can take the means of this essentially histograms as the true parameters if you have, in case we have many readings. So, so now we are looking at the finite element densities. So now, I mean, this is our, I plotted many things here, and these are many computations. Okay, so if you look each row, okay, so we have first row 4 locations, second row 11 sensor location, and third row is 33 sensor locations. Okay, now we look at columns, right? One reading, each first column is 1 reading, second column is 10 readings, and third column is 100 readings. Okay? And then I've plotted this prior finite element density in blue before knowing any data. And this is obviously the prior is in all cases the same. So the blue line and the blue shaded area in all cases is the same. And then we have here the dots, right? And dots are kind of sensor readings, okay? And now I've plotted here the updated finite element density, which we computed using this Bayes formula. And you can see now, I think if maybe we look at the, so in this case, so we have 4 sensor locations and 1 reading at each location. So 4 readings, 4 dots in total. And so the you can see after 1 reading already, this the finite elements solution is updated to this red curve, so which is closer to the sensor readings. And in addition to that, also it's 95% confident region becomes smaller. And if we look now to the extreme case, to the right bottom, so we have here 33 sensor locations, and at each we have 100 readings. So we have many readings, many locations. And you can see here essentially that this finite element solution, the updated finite element solution kind of converges to a mean of a true system behavior, which I showed on the 2 slides before. Right? It has this wiggly shape, and its covariance goes to 0. And now we look at the true system density, and here, I mean, essentially we again in each column the number of readings is constant, and each column is the number of sensor locations is constant. So like in the previous slide, essentially, and the blue curve and the shaded region is the prior density, finite element density, before seeing any data, real data. And this is now the black line, and this gray region is the inferred system behavior, inferred true system behavior. Okay, and if we now go to the extreme case, here at the right bottom, so you can see here that this converges to the mean converges to the real system behavior, and then the variance also converges to the real system behavior. There are some differences here at this region, at the boundaries, and this is related essentially to our assumption about this mismatch error, about the model reality mismatch, the random vector D and its covariance structure. But this can be improved. So now maybe something more relevant for practical engineers. I mean, obviously, the previous example was important to make sure that everything is converging as intended, okay, that the things are consistent. But which is, I think, important also for to have consistent or coherent methods is also important for practical engineering applications. So this is a Staffordshire railway bridge. And this is I'm sure most of you know this much better than me. So this is a half-through bridge located along the West Coast Main Line. And this has been instrumented by CSIC with integrated fiber optic monitoring system. And this has been extensively studied by Liam, Mohammed, Cam, and others at CSIC. And most of essentially the data and the geometries and so on which we are using are from the papers which we wrote. Okay, so this is our structural system. This is our bridge, and this is how the structural system looks like. It's there are two longitudinal main girders, I-beams, and there are multiple cross girders in between, and a concrete deck on top of that. The span is about 27 meter, and the width is around 7.3 meters. So it's a relatively small bridge, I think. Okay. So this is our finite element model which we created. And so in our finite element model, we model essentially all structural members as plates which are rigidly connected at the essentially they can transfer moments, and the plates we discretize with isogeometric B-spline finite elements. So this is something which we developed, but you could use here, of course, also commercial software. And our mesh consists of 4,600 quadrilateral elements. Boundary conditions are simply supported, and we have moving loads due to a passing train. So the train speeds are around 130 kilometers per hour. And in this problem, we essentially neglect the inertia effects. This is the same like in papers by Liam, Mohammed, and Cam. They also neglected the inertia effects. So we compute sequence of problems with by putting the load at different places. So we don't have any vibration or something like that. Okay. So this is how it looks like. This is a movie which should play, right? So you see now the train axis moving, right? Okay. So first, we are comparing now the finite element strains versus the measured strains. And we are considering a top and bottom flange at the midspan. So here we are here at the midspan. We are looking at the top flange and the bottom flange, and we are looking at two strains. And here you can see the strain plotted over the time. So the upper curve is essentially the top flange where we have compression, right? So the blue crosses are the registered or observed strains, and this red line is our finite element results. Okay? So you can see this essentially oscillations in the strains depending where the axle of a train is, like in the previous movie. Okay? So in the bottom, you see these are essentially the bottom flange where we have tension, right? These positive strains. So I mean, I think here the finite elements, the agreement between the finite element solution and between the measured strains are quite good. I mean, surprisingly good. I mean, there are some differences here. I think if you're timing, maybe the train speed, the exact train speed and the assumed train speed are not correct. I don't know. And here on the left, you see essentially free times, the deflection of a bridge at free time instances, 1 second, 2 seconds, and 4 seconds, and which are also indicated here by dashed lines. Okay? So now we are looking at this free time instances. The strain in the top and bottom flange along the entire girder. So along the entire main girder, there are, I think, 20 sensors. So we are looking at the specific time, the strains at those sensors. So, I mean, this is a quite dense diagram, but let's start with this, look at these blue ones, right? So here, so we have essentially the strains in the top flange, right? And this plus signs are the measured strains. And then we have this blue is our finite element result, and the blue line, so prior finite element result. You can see there is quite some difference between the measured and the finite element results. And then the black line is essentially the mean of a updated or posterior finite element density, which seems to lie between the finite element result, prior finite element mean, and the measured strains. So this is what we want, right? So we want to merge them somehow in a coherent way. And I mean, you can study more. I mean, if you look this one, for example, I mean, we have so the red. So this is now the bottom flange at time t 2 seconds. So the plus signs are the measured strains. The red line is the prior finite element result, the mean of a prior without seeing the data. And the black line is after we see the data. So you can see here again that we achieve our updated finite element results are somewhere in between the measured and the prior finite element results. Okay, I think this is should be clearer now, hopefully. Okay, so this essentially concludes my presentation, and I just want to briefly summarize. And so we introduced the statistical finite element method, which allows us to coherently synthesize observation and finite element data. And we postulate a statistical data generating model, which is able to take into account all uncertainties in a data, model parameters, and the model, the physical model, it's the choice of a physical model itself. And so the uncertainties are modeled as random variables, and we use Bayesian Inference to update these random variables and parameters after we see the data. And we use a finite element prior, a conventional probabilistic finite element method in order to obtain the prior finite element solution. And I think using this finite element prior allows us essentially to operate with a limited of data. So we can already get good solutions with a limited amount of data, because our priors are usually in practice are relatively good. So, and then our method is consistent in the sense that if we increase the number of observations, we are able to discover the real system or true system density in case of this synthetic problems like I showed you. Okay, so I mean, this is some aspects of our work, and there is more in it, and we have a recent preprint which is listed here, and I can send you also the copy of that. So I mean, we discuss more, we use this proposed statistical model essentially for in that paper for many other different purposes. And if you're interested, I am happy to talk to you in person later. So thank you.